All right, this video is for Unit 7, Day 4. We're going to continue working with log properties today. Last time we talked about the three properties of logarithms, the product rule, the quotient rule, and the power rule. We're not doing any new properties today. These are the only properties of logarithms, but we'll just be doing more complicated situations that involve maybe more than one rule at the same time. We will also today be doing, like last time, sometimes we'll be expanding, sometimes we'll be condensing. We're going to start with expanding. So here are two logs, log of 2x to the 6th power and log of, and in this case we have a 2x and it's all raised to the 6th power. So these are really similar, but a little bit different in their order of operations. So on this log we have 2 times x to the 6th. So when I'm expanding, I would start by expanding it into a log of 2 plus a log of x to the 6th. But then I could also use the power rule on this second part and bring that power down as a coefficient. So it's log of 2 plus 6 log of x. So that would be expanded fully. And the rules, again, the rules are the same. I used the product rule and I also used the power rule. We just had to use both rules this time. And that's all that's different from today and last time. Last time we kept it with just one rule at a time. So this other log is a little bit different, but not a lot different. It's just that the order is slightly different. So in this case, since the 6th power applies to both the 2 and the x, I would start by bringing that power down. So it would be 6 log of 2x. And then as you expand that further, it would be 6 log of 2 plus 6 log of x. That 6 applies to both parts when we expand it. I guess if you were writing it out step by step, you would maybe write that it's 6 times log of 2 plus log of x. And then maybe you would distribute that 6 to both of the logs. Typically, maybe the first few times you would write out more steps, but once you start doing a lot of these, you can usually just write the answer because you'll get used to thinking about that order in your head. So here's a couple more to expand. Again, these are a little bit similar, but the order of operations is a little different. In this case, I would use the division rule. So we have the log of 2x subtract the log of y. And then we could also expand this product. Log of 2x would be the log of 2 plus the log of x. And then we still have this minus the log of y. So I expanded this into these two logs that are being added together. So again, sometimes you can look at this very first log and see that it's going to be the log of 2 plus the log of x minus the log of y. The next one is the log of 2 divided by the quantity xy. So if we expand this, this would be the log of 2 subtract the log of xy. And let me make this one a little smaller. And then we could expand this part to a log of x plus a log of y. So you have the log of 2 subtract this expanded logarithm. So that negative applies to both parts. It'll be the log of 2 minus the log of x minus the log of y. And again, a lot of times people get used to going straight from here to here. They see that the 2 is on top, so that's a positive log. That's the one that starts. And the x and the y are both on the bottom, so they both end up being subtracted. So you'll, after a while, probably be able to skip straight down there. It's common for people to maybe miss that this is negative and write that it's positive, but that subtraction applies to both parts. Essentially, if it's in the denominator, that is going to be a subtracted log. If it's in the numerator, that's a positive log. A couple more to expand. We have a 7 times an x times a y to the third. So it would be the natural log of 7 plus the natural log of x plus, I'm going to have a natural log of y. It has a third power right now, so I could bring that power down as the coefficient. So this would be my final answer. Natural log 7 plus natural log x plus 3 times the natural log of y. Another one, log of, we have a 10x squared divided by a yz. So if we expand that, I'm going to do this one in 2 steps. We have the log of 10x squared minus the log of yz. And if we expand the log of 10x squared, that would be the log of 10 plus 2 times the log of x. So I brought my second power down. And if we expand this log of yz, both of those are going to be subtracted, the log of y and the log of z. In part because that negative sign would apply to anything inside there. And there's actually one more thing we could do to simplify that, and that is this very first log. This is the log base 10. Log base 10 of 10 is 1. So it's 1 plus 2 times the log of x minus the log of y minus the log of z. Okay, one more expansion. The natural log of the cube root of x to the fifth. Remember that roots are another way of writing rational exponents. So this is exactly the same as the natural log of x to the 5/3 power. So if we expand it, it would just be 5/3 times the natural log of x. Okay, so here's one way that you might use expanding. On the graph is shown function f of x, the log base 2 of x. I want to know which basic transformations we could use to graph g of x, or how is g of x different from f of x? Well, it looks quite a bit different. They're both log base 2's, but this one has just an x, and this one is an 8x squared inside the log. So if we expand that, we have the log base 2 of 8 plus, and if we use the power rule, that would be 2 times the log base 2 of x. Well, we know what this is. This is log base 2 of 8 would be equal to 3. So it's 3 plus the log base 2 of x. And another way of writing it, which might look more familiar, would be to put the log first, 2 log base 2 of x, and then add the 3. So the 3 being added at the end tells me that the graph is shifted up 3, and the 2 tells me it's stretched by a factor of 2. So if I compared these two, stretching it just means that it's going to be sort of twice as tall, if you want to think of it that way. It's stretched by a factor of 2, and then so that one's stretched, and then the plus 3 means that it would shift it up 3. So it's more like this. The green one would be g of x. I just showed the stretch in between because sometimes it's easier to think of the stretch, what the stretch would look like, and then think about shifting that up or down. All right, so these two graphs are really closely connected, even though they don't look that connected. It's just shifted up and stretched. This is another really common way that expansions can be used. And this one is sort of historical, back when they used to look up things on a table. So if we know that the log base b of 5 is 0.732 and the log base b of 11 is 1.091, we can approximate the values of these other logs quite easily. If we expand it first, That's what we're going to do is expand. So if I expanded this, it would be the log base b of 5 subtract the log base b of 11. So the log of a quotient is the difference of the logs. So we subtract the two. Well, I know what this quantity is. Log base b of 5 is 0.732. And I know what this quantity is. It tells me that that's 1.091. So all I need to do to find the log of 5 over 11 is subtract them. And that would be negative 0.39559. So this next one, log base b of 55, I could find that one by expanding it, by thinking of that 55 as a 5 times 11. So when I expand it, it becomes log base b of 5 plus log base b of 11. So the only difference here is that I'm going to add them. Log base b of 5 is 0.732. Log base b of 11 is 1.091. So log of 55 would be 1.823. The last one is log base b of 125. Well, we want to try to figure out how to get that 125 using 5s and 11s, and probably the easiest way would be 5, or maybe the only way, would be 5 to the third power. So if we use our power rule to expand that, it would be 3 times the log base b of 5. So I'm just bringing that power down using the power property of logs. So I know what log base b of 5 is. It's 0.732. So all I need to do is multiply that by 3. So that's 2.196. Okay, this is really exactly the same, but for some reason, when it has variables in it, it's a lot harder for people. We know 3 logs. We know the log base b of r is 2, we know the log base b of s is negative 3, and we know that the log base b of t is 5. So we want to know what's the log base b of rst. So again, we're going to use expansion to help us here. We're going to expand each of these logs. So if I expand the log base b of rst, this is multiplication happening here, r times s times t. So when we expand it, it becomes the addition of logs. Log base b of r plus log base b of s plus log base b of t. And here's where people sometimes get tripped up. They want to put the 2 right here for r, because they see right here r equals 2. But it is not that r equals 2. It's that the log of r is 2. So wherever you see this quantity, you can replace that with the number 2. Wherever you see log base b of s, you can replace that with the quantity negative 3. And wherever you see a log base b of t, you can replace that entire quantity of that log with the value 5. So it's 2 plus negative 3 plus 5, and when we add that up, it is, I'm thinking, 4. So the log base b of r times s times t, rst, is equal to 4. So let's try this one. Log base b of t to the third over rs squared. So if we expand that, I'm going to expand it in one step, but I've got a t to the third in the numerator, so that's going to be a 3 times the log base b of t. I have an r in the denominator, so I'm going to subtract log base b of r. And I also have an s squared in the denominator, so it's going to be a subtract, because it's in the denominator. I'm going to bring the power down, log base b of s. So now I'll substitute the values I know. I know log base b of r is 2. I know log base b of s is -3. And I know log base b of t is 5. So this will be the same as 3 times 5, subtract 2, subtract 2 times -3. And that would be 15 minus 2, and this is actually going to be a plus 6. So I think that adds up to, what, 19? So the log base b of the quantity t to the third over rs squared is equal to 19. Make sure when you're doing these that you don't substitute the numbers in for the letters. It's not that r is 2, it's that the whole log of r is 2. So that's sometimes a little tricky. So now we're going to switch to condensing. Same rules, we'll just go in the other direction. Can we condense a complicated set of logarithms into a single logarithm with an exponent, or sorry, with the coefficient of 1? So first for this one, I would bring that power up. So I have a log of x plus a log of y squared. And then if we condense that, it's going to be the log of x, y squared. When you add two logs, it becomes multiplication of the argument. So in this one, I would first bring my power up. That's going to be a y to the 5th. This is going to be a 3 squared. And if I use my subtraction rule, this would be the log. So I want it to be a single logarithm. And it's going to be a y to the 5th over 3 squared. Probably it would be even better to go ahead and write it as y to the 5th over 9. Okay, so we're just condensing like last time. We're just doing multiple rules together. So here we have log base 3 of 4 plus 5, log base 3 of x, subtract log base 3 of y. Well, if I condense that, log base 3, I would probably bring this power up first. So that's a 5th power of x. And so this will be a 4 and an x to the 5th. And then we're subtracting the log of y. So this is going to be over y. And that is one argument, one log. Condensing means you have one log. A common error that I see sometimes people make is to write this. Be really careful there. When you're condensing, the rule tells you you're only going to have one logarithm. It's not take a log and divide it by another log. It's the log of a quotient. So be careful, only one log. All right, another one, 7 times the natural log of x minus 6 times the natural log of y plus the natural log of z. So this is going to be an x to the 7th power. This is going to be a y to the 6th power. So it's a natural log. It's going to be an x to the 7th. We're subtracting the log of y to the 6th, so that's going to be in the denominator here. And then we're adding log of z, so we want to times this argument by z, so something like that. Natural log of x to the 7th is z divided by y to the 6th. One log, all condensed. Another one, so natural, let's see, sorry, not natural log, regular log. Log of x plus the log of x minus 5. Well, my addition rule for logs is that I times these two arguments together. So this would be an x times an x minus 5. You maybe would want to show it like this, or another way of writing it would be x squared minus 5x, if I distribute that x to each term. Now, don't get confused about trying to separate this into division now. This is the log of a quantity that happens to have subtraction in it. But we don't have a rule for any way of simplifying what it looks like now. Okay, let's try another one. The natural log of x squared minus 9, and we want to subtract the natural log of x plus 3. So this subtraction here tells me I can condense the logs using the quotient rule, like so. And if you remember, x squared minus 9 is the same as x plus 3 times x minus 3, so we could actually reduce that. So it becomes the natural log of x minus 3. So those are the two condensed expressions. Condensing, we will use, let me go back to this for a second. We'll use this idea of condensing sometimes when we solve equations. So next time on day 5, we'll use condensing a lot more. Okay, so now for something completely different. Log base 2 of 8 we know is 3. Log base 2 of 16 we know is 4. What about log base 2 of 12? Eek. Your calculator doesn't have a base 2 log button. It has two log buttons. It has log base 10, which is the LOG button, and it has the LN button, the natural log button, which is base E. Your calculator can't tell you what log base 12 or base 2 of 12 is, at least not with a specific little button. But it turns out there is a way to find out what log base 2 of something is, or log base 4, or log base 6. And we can use this formula called the change of base formula to evaluate logs with bases other than 10 or e. So our calculator knows base 10, our calculator knows base e. This can help us with other bases. So it just says that if you have log base b of a, it's the same as log base 10 of a, so you could use your calculator button. And we have to divide that by log base 10 of b, of the base. So it turns it into base 10 logarithms. So if I wanted to know what's log base 4 of 300, I take the base 10, log base 10 of 300, and I can use my calculator to figure that out. And I divide it by the log base 10 of 4. And you can, if you use your parentheses right in your calculator, type that in all at once. It would be the log of 300, end your parenthesis, and then do divide by the log of 4 and end your parentheses. So this one is about 4.11. Log base 3 of 6 would be exactly the same as the log of 3. So whatever the argument is, that's the one that goes on top. That one's on top, and the base, it's a little bit lower, it goes on the bottom. Sometimes that helps people remember. So this would be the log of 3 divided by the log of 6. Just make sure you use your parentheses correctly. So this one is 0.613. Just as maybe a little bit of an aside, this actually works for any base. We typically use base 10 because our calculator knows base 10. You could just as easily use that natural log button, and it would give you exactly the same answer, which is 0.0613. Last one, this would be the log of 9 and divided by the log of 2. Log of 9 divided by log of 2 is the same as 3.169. Probably we would just say 3.17. Okay, so change of base is pretty handy, but please be careful that this is not the log of 3/4, which we could expand to the log of 3, subtract the log of 4. These are very different things. This is what we would use for change of base. This would be the same as the log base 4 of 3. So be careful there. Those two things mean very, very different things. Make sure you're paying close attention to which case you have. Also, sometimes people confuse this. we have this log rule. It is always true. It's a good log rule. That doesn't tell me anything about this. Log of a plus b, you would have to figure out what a plus b is, and then you could maybe do something. But these two things are not the same. Not the same. Make sure you know what you're dealing with as you're dealing with logs. So we're going to do one more. Log base 4 of 25 times log base 5 of 4. Well, if we use our change of base, this would be the same as log 25 over log 4. And this would be the same as log 4, and we would divide by log 5. So we could actually reduce that to log 25 divided by log 5. And if we were being super fancy pants, we could rewrite that as the log base 5 of 25. So the base would be the one that's lower, and that is exactly equal to the number 2. Okay, we're going to condense one more. We want to condense this expression, but we can't because the two logs don't have the same base. But we could use change of base formula to change this log into the same base. So I'm going to leave the log base 3 of x alone. If I change the base of this second log, it would be the same as log base 3 of x divided by log base 3 of 9. So now it's in base 3, but hey, I know what this is. Log base 3 of 9 is exactly the same as 2. 3 squared is 2. So log base 3 of x, it would be plus, this is a 2 in the denominator, that would be plus 1/2 log base 3 of x. So I could add those two quantities together now. The log of x plus half of the log of x would be the same as 3/2 log base 3 of x.
Students, just a reminder that we're selling tickets to Junior Prom at the
And that is it. And of course, there's another way you could write this, which would be the log base 3 of x to the 3/2 power. That is it. So we just practiced condensing and expanding a little bit more complicated expressions today, and don't forget change of base rule.